Example problem 8.1 asks for us to find the first derivative f prime at the point x equals 1.3. Oops. Asks us to find it three different ways. First using the 3-point forward difference formula, next using the 3-point backward difference formula, and then lastly using the 2-point central difference formula for these points. Pretty straightforward process. We'll be looking at the 1.3 point as the derivative location, and of course we'll be referencing the large chart of equations on page 318, 319 of your textbook. I think the first two equations are actually on 317, and that's the one we need initially, the 3-point forward difference equation. So this says f prime of x at a particular location is negative 3 times f of xi. So between the forward difference, we'd start at x3, which if you note my handwritten arrays up here are not vertically aligned, but still each 5 elements. So that would be negative 3 times 0.9716. The second element, going by equation at the bottom of page 317, is 4 times the functional value of x of I plus 1. So that would be 4 times 1.1814. And then the formula lastly says minus 1 times the plus 2 element, which would be 1.4117. All of this divided by 2h, which h in this case is 0.1 because that's the step size between our x values. So 2 times that would be 0.2. We should be set to calculate a final derivative value of 1.9955. So f prime of x, again at 1.3, using now the 3-point backward difference formula, is actually described on the next page, and really it just changes which point you're referencing. It doesn't even really change the coefficients. They're shifted around in order slightly, but not a big deal. So f prime of x for the 3-point backward difference formula would be f prime of x of I minus 2. So this is where the single weighted coefficient comes from. So that would be 0.6133, looking at our data set. Yep, so that's the first element. We're going back in space, in our spatial dimension, 2 spots, minus 4 times the minus 1 term, so 0.7822, plus 3 times the term we're at, 0.9716, all divided again by 2h, so 0.2 for the same reasons. And that gives us a derivative value of 1.9965. So ever so slightly different in the thousandth decimal place than the forward-looking difference. And then lastly, we do the central difference formula, which really just looks 1 point ahead, 1 point behind. So f prime of x equals 1.1814. That'd be the I plus 1 term minus 0.7822. That's the I minus 1 term divided by twice the step size, so 0.2. Gives a derivative value of 1.9960, which lies directly between the two values we've otherwise predicted. Makes sense if you think about it. The central derivative lies centrally between the two other derivative values we're concerned with. So those are 3 different ways of calculating the same derivative value at one given location. To say which one is the most correct is a difficult sell. They will each fit a different type and area and placement of a problem in a better way. But just going straight by the predicted order of error magnitude, the central difference has a predicted order of error of h squared, while the other two look like they're also h squared. So the fact that you're using 3 points for the forward and backward difference, and then total really just 2 points for the central difference, mean that their order of error ends up on the same scale. So a very simple process, really just find the correct equation, all of them derived by Taylor series expansion, and you're pretty much set to go.